Okay, let's get this show moving. So differential equations are equations that have derivatives in them. They're ordinary when the derivative is with respect to a single variable. If you have two derivatives, then you have partial derivatives, and they're called partial differential equations. So if you're a mechanical engineer, you'll have to study those for your fluids and things like that. Some of the thermodynamics problems are naturally set up with partial differential equations. In robotics, we don't see too many of those until you start working on compliant beams and things like that. Then partial differential equations could come in. But place to start, ordinary ones. Okay, so we went through some ordinary differential equations that we could solve by the method of separation of variables, and probably half of the nonlinear differential equations that have solutions can be solved in that way. But there are many nonlinear differential equations, and this was simply taking a parachutist and adding a nonlinear drag to it. The solution cannot be given with elementary functions, and so you really need to understand numerical methods in order to compute solutions to nonlinear ordinary differential equations as a general rule. Now, just computing solutions would leave us without the insight we need in order to build systems from scratch, in order to understand qualitatively what things are going to be doing, in order to be able to understand if our numerical solutions are actually correct. So we'll be working on some of the qualitative insights shortly. And the way we will do that is by learning to understand solutions of linear differential equations quite deeply, and then we'll understand to what extent linear differential equations can be used to approximate solutions of nonlinear differential equations. The standard form in which the solvers want to see the equation is the same one that all of the theoretical methods for analyzing differential equation use. It's called first-order ODEs. And it's because there's only a single derivative here, but what makes it a rich class of models is that X is a vector. And the way those systems come about is, for example, this was taking a pendulum which had a second derivative. The acceleration was equal to minus g over L times sine of theta, and adding a simple DC motor to it and modeling the current through the windings of the motor. And then you get a third order differential equation where order is the highest derivative that appears in the differential equation. You can rewrite it in the standard form by introducing what are called state variables. The fact that they're called state variables is not too important to us, but you'll hear that term. And so we set this first variable equal to x1, its derivative x2, its derivative x3. And then we stop there because the highest order derivative, we can always solve for it in terms of the lower order terms in the model. So theta triple dot is minus a2 theta double dot, etc. And when you do that, you get a simple structure of the differential equation because x1 dot is theta dot, and theta dot is equal to x2. So x1 dot is x2. x2 dot is theta double dot, but theta double dot is x3. So that part fills in a very straightforward manner. And then you take x3, its derivative, in this case would be theta triple dot And as I mentioned, we just solve for theta triple dot, and then we plug in the parameters, and we would get minus A0 times x1, minus A1 times x2, minus A2 times x3, plus a constant times the motor voltage for this example. And this gives us x dot, here's the x, equals f of x, and here's the f of x. This is f1 of x, f2 of x, f3 of x, etc. So that's a vector first order differential equation. You can do the same thing with the robot equations, which naturally appear as a vector of second order derivatives. And you simply define x1 as a vector of all of the generalized position variables, and x2 is the generalized velocity variables. And so x1 dot is q dot, but q dot is x2. So that part of the differential equation is just like when we were working up here. And then the second part of the equation, x dot is q double dot. And we can solve this equation for q double dot. And the only thing we do is we try to avoid inverting this matrix, because for typical professional quality robots, let's say, that matrix becomes large, 20 by 20 or more. And we don't want to compute its inverse numerically. And so we'll just solve for q double dot given q and q dot and the terms in the model. And that's what this does. Okay, so that's just how we rewrite equations in the form x dot equals f of x. Sometimes we have to introduce auxiliary coordinates in order to do it, but it's pretty standard. Now, differential equations, when they're nonlinear, they can exhibit some interesting behavior that you might not have anticipated. This one was set up so that when we do the separation of variables, we get dx over 1 plus x squared, which gives us arctangent of x when we do the antiderivative, and we get dt on the other. And when you do all the algebra, the solution for this equation is x of t equals tangent of t. And if we start at the origin at time 0, we know tangent blows up at pi over 2. And that is termed finite escape time. So the solution simply ceases to exist at pi over 2. Infinity is not an allowed number, okay? It's not a real number. And then there's this funny differential equation with x to the 2/3, it looks innocent. It doesn't have 27 terms on the right-hand sides with exponentials and logs and sines and cosines going crazy. It's simply x to the power 2/3. But you can check that it has an infinity of solutions. So for every constant c greater than 0, this function is a solution. And we saw a video where that could be interpreted as a ball sitting on a mound, and then at some random point in the future, the value of c is chosen, and then you get the solution starting at that time. So, kind of mind-boggling, to be honest with you. We have packages, the differential equations package in Julia to get professional quality solutions. But if you're ever working on a small robot where you don't have those packages available, Euler's method is quite easy to implement. And you just write down your favorite definition of the derivative and plug it in here and solve for x at t plus delta t. And you get the same formula you would get if you're doing Riemann integration and you're doing the left Riemann sum. So that's Euler's method, so it's from the 1700s. And before we get going on new stuff, let me just get the QR code out of the way. Are we good? I see a few little photos being taken still. You guys are good? I don't know, for some reason all the TVs are working, so you're surrounded by QR codes. Okay, everybody online got it? Good, thank you for letting me know, I appreciate that. Okay, so for today, we're going to do more on solutions of differential equations. Ordinary differential equations. We always just call them ODEs. And a key thing we're going to be asking ourselves is, when do solutions exist? And if they exist, when are they unique? And in terms of existence, solutions can exist for a small period of time, like between 0 and anything short of pi over 2, or they can exist for an infinite amount of time, like the pendulum. It'll just oscillate forever. Okay, so existence has interesting twists on it, and it would be nice to know when our equations have a unique solution so we can actually make predictions about the future evolution of the system. In this one, it's a little hard because we have no clue which value of C nature is going to be drawing. So if that's your model, you're kind of in trouble for making predictions about what's going to happen. A little bit like the weather. Okay, so for our warm-up, let's verify that x of t equals cosine of t minus sine of t satisfies the ordinary differential equation x dot 1, x dot 2 equals 0, 1, minus 1, 0 times x1, x2 with initial condition at time 0 being the first natural basis vector. Okay, so the first thing to remind ourselves is, what does it mean that a function of time, this one, for example, is a solution to the ODE? First thing to check is x at 0 satisfy the initial condition. Second thing to check, I plug x on the left, that means I compute its derivative. I put x on the right, so I'm going to multiply by this matrix 0, 1, minus 1, 0, and I need left-hand side equals right-hand side. It's that simple. Okay, so solution. I want to do this enough so that it becomes automatic. So check the initial condition. Okay, so x at 0, that's supposed to be cosine of t minus sine of t evaluated at t equals 0. Yep, not very hard. It's 1, 0, and that equals x0. So I should define this to be x0. So it satisfies the initial condition. Check. B, does it satisfy the ODE? Well, it has a left-hand side. So we need to compute d by dt of this proposed solution, which was cosine of t minus sine of t. Since it's sine and cosine, this is almost mechanical. D by dt of cosine minus sine of t. D by dt of minus sine of t is minus cosine of t. The right-hand side of the differential equation, we have the matrix 0, 1, minus 1, 0, that has to multiply x of t. Okay, so we use the finger tracing method. So 0 times cosine plus 1 times minus sine is going to give us minus sine at the top over there. I'll write that in a second. And then we do the finger tracing method again. We get minus 1 times the cosine and 0 times the sine, and we add all those up. And so this is minus sine of t, and then minus 1 times cosine of t. And we have left-hand side equals right-hand side. So it's a solution. It's that simple. It's that mechanical. So someone proposes a solution to you. It's similar to someone proposing a solution to a quadratic equation or a cubic. You just plug it in, and if you get 0 on the right-hand side, it's a root. Here, plug in t equals t0. Do you recover the initial condition? And then differentiate the proposed function, plug it into the right-hand side, compare left-hand side and right-hand side, they're equal, you're done. Okay? That's a solution to an ODE. Let's do one more, but I'm not going to make you write it out because it's just kind of boring, okay? I think you get the hang of it. Ooh, where to go? Well, we will, maybe I'll find it here real quick. Let me try. Nope, it didn't cancel. It didn't transfer over. So I'll just put in the ODE and let you check everything at home. Verify that phi takes 0 infinity to R2 by. So I'm writing the solution a little bit differently. One over t plus 1 squared and minus 2 over t plus 1 cubed is a solution to x dot 1, x dot 2 equals x2, 6 times x1 squared with x at 0 equal to 1 and minus 2. Okay, so I'll let you do that at home. It looks like there exists. Let's make it a verify. Verify that function. So plug in t equals 0. It's easy to see in this case with 0, 1 over 1, minus 2 over 1 cubed is minus 2. So the initial conditions, it's a little bit more work to do all of the derivatives and put phi dot on the left-hand side here, and then to put phi 2 and then 6 times phi 1 squared and see if left-hand side equals right-hand side. Okay. Question. Could there be other solutions? I've just proposed one. Okay, so at home you'll go through and verify that. But the same thing here. Okay, so you're used to, for example, if you have a polynomial and somebody gives you one solution, you're not surprised when someone else gives you a second solution, okay? So there's lots of equations where uniqueness of solutions is not inherent. And what we're going to see for differential equations is that the non-uniqueness is fairly rare, at least for things that matter to engineers. Okay, we will paste this in so that you don't have to write it in, but you can just get it from the book. So this is the official definition of a solution of a differential equation. Come on. So we have our differential equation, has an initial condition. Function phi, which is vector valued but depends upon the scalar variable time, is a solution if it is continuous, meaning each of its components, so it has a phi 1 and a phi 2 and a phi 3, those are all continuous functions. It satisfies the initial condition. So phi at t0 is x at 0, so it satisfies the initial condition. And then if you compute the derivative of the function and put it on the left-hand side, you plug in the function onto the right-hand side, they're equal. So it satisfies the ODE. And then this is just a small note, but we typically know when we write x dot that t is there, so we just drop it. We just write x dot equals f of x. So that's the common notation. So we don't drop it to try to cause confusion for beginners. We drop it to make the formula shorter, that's all, okay? So it's not, we're not trying to trick you, Katie, okay? But okay, so the thing I want to spend time on going through is conditions for the existence and uniqueness. We've seen equations where solutions blow up in a short amount of time. We've seen equations that have nicely defined solutions like sine and cosine. We've seen others that have infinite number of solutions. And so what we'd really like to have is a simple criteria to say, this differential equation in front of me has a solution. That's the existence question. And there's only one solution. So I work hard, I find a solution, it is the solution. So that's what we're after. So consider a vector ODE. X dot equals f of x, where I've dropped time as I promised. And we set some initial time and some value. And to let you know it's a vector, I'll underline that the initial condition is in Rn. Okay. First thing will be local existence and uniqueness. And then we'll do a global version. Okay, so the picture to have in your mind when we're talking about local is this one right here. We start at the origin at time 0. The solution exists, but then it ceases to exist at a finite time. So the solution is local in time. Local in time. Okay, so the first condition we're going to have is to guarantee that the solution exists on a small interval of time. The next condition we'll have will be for solutions like this that exist for all time. That's said to be global. So that's what this proposition is going to be broken up into two pieces. Just saying a solution exists on a small interval of time and then on a larger interval of time. So if for some radius r positive, and it'll be about the initial condition, the Jacobian J sub f of x by definition equal to that matrix of partial derivatives, first partial derivatives. So if that Jacobian exists, meaning the function on the right-hand side of the differential equation is differentiable, exists, and the functions there are not too wild, they're continuous. If they're also differentiable, even better, but they don't have to be. They just have to be continuous. They don't have to be continuous on all of Rn. They just need to be continuous near the initial condition. So for all x's such that the norm of x minus x0 is less than r. So that's within r of the initial condition. So if that Jacobian exists and it's continuous near the initial conditions, then there exists a local solution. More precisely, there exists delta positive such that the ODE has a unique solution on the time interval t0, t0 plus delta. Okay. This is what we mean by local. Small interval of time beyond the initial time. Okay, let's see how this works on that equation that has tangent as its solution. We have 1 plus x squared. The initial time was 0, and the initial value was 0. It's a scalar r. And we computed that x of t is tangent of t. And it blows up at pi over 2. So the solution ceases to exist at pi over 2. Okay, and that's because it has escaped to infinity, is what we say. So to apply our method, we would have to compute the Jacobian, which is d by dx of 1 plus x squared, and that's just 2x. So it's perfectly continuous. Not just near our initial condition, of x0 equals 0. So you could take any other initial condition, pi, 3/4, 200, minus 368. You could take all those initial conditions and the solution will exist for a small interval of time. So, conclusion. That and a function that goes from t0 to t0 plus delta 2r, that satisfies the ODE. Okay, so that's what we get from the Jacobian being continuous. This function exists, and it satisfies the ODE. Moreover, it is unique. There's not another solution. Okay, so this is super powerful. You just calculate a Jacobian and you look, is it a continuous function? Doesn't have any jumps in it, near the point of interest to us. Now, how big is delta? We don't know, okay? Because back here, we have the solution in closed form. We got lucky, the method of separation of variables gave us the solution in closed form. We know delta is equal to pi over 2 when we start at x at 0 equals 0. If you were to start at a different initial condition, delta will be shorter, okay? Because it's going to start from there and still blow up at pi over 2. And if you get closer and closer to pi over 2, your delta is going to get smaller and smaller. And then the solution to this equation, you just take the pi over 2 and you translate it, and that's what you have going. So if you take an initial condition over here, it is going to exist for, some of the time it takes to get to the origin, and then it's the pi over 2 that it takes to keep going. So we don't know a priori how big delta is. The theorem doesn't tell us. Okay? It just assures existence. Okay, let's take another crack at this. Global, and that's going to mean that the solution exists for all time t greater than 0 and any initial condition. If there exists some constant L that is finite, such that for all values of x in Rn, so I calculate the Jacobian, each of its entries. So the I is the row in the function on the right-hand side of the ODE. The J is between x's 1, 2, 3, 4 to n. So this is the max over all of those indices in the n by n matrix that is the Jacobian. So if the Jacobian is bounded, the ODE has a unique solution on T0 infinity. So the solution can be extended for all time, and that works for any initial condition in Rn. Okay, so I imagine it's going to take us a little bit of effort to understand this condition, but the main thing is its power lies in the fact that we don't need to solve the ODE to test this condition. We just need to have the model. We calculate first derivatives, and if we can bound them, then we get global existence and uniqueness of solutions. Okay. So here's an example of how that works out. X dot 1, X dot 2 equals X2 minus sine of X1. Okay, do we recognize this model? Yeah, so it's the pendulum, okay? So we suspect solutions exist because we know these things either oscillates or if you go really fast, it spins round and round, but it can't go anywhere, okay? It can't blow up. So we'll just calculate the Jacobian. So this is f of x. What does the Jacobian look like? It's df dx1, df1 dx2, df2 dx1, df2 dx2. Rarely would we do these by hand, okay? But on these simple examples where we're trying to learn what's going on, we do it by hand. Okay, so what's the partial derivative df1 dx1 equal to? Give them to me, please, okay? First one is 0. Second one, you guys don't want to help? What's df1 dx2? Any ideas over here? 1, yeah. Okay, so that's the first row. Second row, we do the partial derivative with respect to x1. Derivative of sine is cosine. And then the partial derivative with respect to x2, 0 again, okay? So we get a lot of zeros. So df by dx1, df by dx2, df2 dx1, df2 dx2. They're all less than or equal to 1 for 1 less than I, j less than or equal to 2. So there's the L. That holds true for all x, because the magnitude of cosine of x is less than or equal to 1. And so, conclusion, global existence and uniqueness. For all initial conditions in R2. Okay, so that's pretty cool. We know a lot about the solution, even though we can't write it down. Okay, so in terms of elementary functions, that differential equation can be proven. You cannot express the solution. You have to use something called an elliptic integral. I haven't studied those very much, I'll be very honest. Okay, so, but yet, by simply checking conditions on a derivative, we can assert existence and uniqueness. For all time and for all initial conditions. So that's super powerful. Let's do a couple more, then we'll take our break. Okay, so this is the equation that has an infinite number of solutions. So we would expect that there's a problem here, okay? Let's just check. So here's f of x. We call it the Jacobian, but it's just the derivative of a scalar. And so by the power rule, that's x 2/3 x to the minus 1/3. And that's 2/3 1 over cubed root of x, if you care, okay? So what's the problem? Well, our initial condition was the origin. And what happens to the Jacobian at the origin is it blows up, so it's not bounded, and hence our theorem does not apply. It doesn't say there exists uniqueness and there exists a solution and it's unique, okay? So theorem, so the limit as x approaches 0 plus jf of x is infinity, which implies the theorem, or excuse me, I called it a proposition. Okay, so we cannot conclude that there exists a single solution or a solution or any solution at all. We don't know anything about this equation from this result. We got lucky and used separation of variables, and you can prove it has a whole bunch of solutions, but you can deduce that it's unlikely to have unique solutions, but you can't deduce that for sure. Okay, so let's take a pause there. And the main thing that we've covered is this conditions for existence and uniqueness. So if you have a differential equation, Jacobian is bounded locally. We get local existence and uniqueness. The Jacobian is bounded globally. The solutions exist for all time, for all initial conditions. It's beautiful. Okay, stop there. So when do they have solutions? When might they not have a solution? That's what we can do. Okay, so the main thing about this is when you're working with differential equations, we now know if the right-hand side is differentiable and it's continuously differentiable, look, the solution will exist for at least a small interval of time. And if that derivatives on the right-hand side are globally bounded, then solutions exist forever. So that's very powerful. The theorem is a special case of the contraction mapping theorem. So the proof is based on the contraction mapping theorem, and that's done in Rob 501. So the grad level math for robotics, and it's covered a little bit less. So in EECS 562, which is the nonlinear control class. So it's not totally out of bounds. There's probably versions of it covered in Math 451. I'm not sure about Math 351, to be honest with you. Okay, so I want to do another example because it's super prevalent and important. So this is x dot equals a times x, where A is a square matrix. And X is a vector. Okay, so here's A. Here's X. So X dot equals AX. So this is the differential equation equivalent of AX equals B, except B is now X dot. So it's a lot more interesting what can happen with this equation. Okay. Claim. I don't need absolute values here. Claim. dfi of x dxj is equal to aij. It's the aij entry of the matrix. So the right-hand side of the differential equation, that's f of x. And so this would be f1 of x to fn of x, right? So x dot equals ax. Very compact, our vector matrix notation. Okay. So what is the ith row here? Because I'm going to take its partial derivative with respect to xj. Well, it's the ith row of A times x. And using the finger tracing method, can someone help me write down? What do I get here? What's the first term? So I take, well, for me, it goes like this. I guess for you guys, it goes like, I can't do it with my other hand, okay? It's impossible, okay? I have to turn around like this. We got to go across the ith row and down x, okay? I'm unable to do mirror symmetry with my hands. I don't know about you, okay? So if this is A11, the first entry here is AI1. It multiplies x1. And then you get AI2 times x2. Then AIN times xn. Because the first entry is the row, the second entry is the column. So if that's fi of x, and now I take the partial derivative with respect to xj, the j just picks off the column here. So this equals aij. Okay, so it's that simple. And the importance is the magnitude of dfi dxj max over I and j is just the max over I and j of the entries of this matrix. And that's always finite, because a max over a finite set is finite. Okay? And so solutions globally exist and are unique for linear differential equations. So x dot equals ax. Solutions to that globally exist and unique. And so those arise from RLC circuits. They arise from F equals ma when you have simple masses and springs without rotating elements to give you nonlinearities, et cetera. So there's tons of examples where these linear differential equations arrive. So question, if the solutions exist, what are they? Okay, so or let me just say, since it's unique, what is the solution to x dot equals ax, x of t0 equals x0. Oops. Okay. Well, we start simple. Let's let a equals little a equals 1 by 1. X dot equals ax. X at t0 equals x0. Just a real number. Okay, what function do you know that when you differentiate it, you just bring down a constant and you get the function back? Okay. I mean, that's what we need. We need the derivative of x is just proportional to the function itself. Doesn't work with sine because we differentiate sine of 2t. Yeah, the 2 comes out from the chain rule, but the sine gets turned into cosine, so it's not 2 times sine of x. Okay? The exponential is the magic one that does this. Okay. Well, how would we show that? It's the usual. Does it satisfy the initial condition? And when we differentiate it, does it satisfy the ODE? So phi of t0 is e to the a t0 minus t0 times x0, which is e to the 0 times x0 equals x0. Initial condition, checked. Okay. Keep reviewing this concept because it's so important. Now we calculate the derivative. So d by dt of e to the a t minus t0 x0. So the derivative of the exponential, we get the a that comes down. I'm going to write the chain rule backwards here, okay? So this function, when we put it on the left-hand side, we put it on the right-hand side, it satisfies the ODE. And it satisfies the initial condition. Okay, so for scalar, it's just the exponential. Can you see where I might be going now? X dot equals AX. X at T0 equals X0 in Rn. Okay, I'm looking for a class of functions that when I differentiate them, I get a matrix out in front. That looks pretty wild, okay? It looks extremely wild. And in Math 216, if you hadn't had a linear algebra course already before you got in there, it would be really tough, okay? And the only thing I'm going to say is, wouldn't it be wild if the answer were E raised to the matrix T minus A times T minus T0 times the initial condition? Okay, so that is going to be the answer, and we're going to have some fun here. Okay, so this is going to be pretty conceptual. We're going to try to understand what does it mean to do the exponential of a matrix, and then we'll try to understand how you would differentiate something like this. That looks pretty wild. It looks pretty wild. Okay, you guys braced? You're holding on? You got your seatbelts buckled up? Okay, there's going to be some twisty turning, some fast racing. Yeah, online, you guys are ready? Okay, so I'm just going to paste in some preliminaries because you'd be bored to death writing them out. Okay, so this is just the Taylor series for e to the x. So you remember the Taylor polynomial, you took the function at a point x0, then its first derivative at the point x0 times x minus x0 divided by 1 factorial, then the second derivative times x minus x0 squared over 2 factorial, etc. So we're taking x0 to be 0 here. And so e to the x, it becomes evaluated at the origin is 1. Its derivative is e to the x. We evaluate that at the origin as 1, so we multiply by x over 1 factorial, and its second derivative evaluated at the origin is 1 times x squared over 2 factorial, etc. So that's the Taylor series. Okay. Yeah. Okay, so here's the infinite sum version. And the convention that's being done here, so when k is 0, you've got x to the 0. So the convention is that's 1. And when k is 0, you have 0 factorial. The convention is that is 1. So that's just a convention. So this e to the at that we were looking at, it can be written as 1. I plug in at for x. I get at over 1 factorial. I got at squared. I've got at to the k over k factorial, etc. And when I multiply those out, I get k equals 0 times a to the k, t to the k over k factorial. And if I want to really just stick it in, fine. I don't have to put t in there. I can put t minus t0. So I just replace t with t minus t0. So that's the Taylor series for the solution to a first-order scalar linear differential equation, x dot equals ax. Okay, so that's just that. Now, I gave you guys a heads up several weeks ago, but I'm not assuming you remember any of that, so let's just do it. I'm going to show you how you take any Taylor series or Taylor polynomial and you can apply it to matrices. So you can do this for sine, cosine, logarithm, 1 plus x. You can do it for all of those, but we're only going to do it for the exponential. So when A is an n by n constant matrix, the convention is that A to the power 0 is the n by n identity matrix. Okay, so in my Taylor series for e to the ax, I did have an a to the 0, and that was 1. That is the 1 by 1 identity matrix. Okay? And so with this, I can make the following definition. I use the Taylor series to define what the exponential of a matrix is. So for A, an n by n matrix, I'm just going to go ahead and define e to the at. So it's by definition equal to. First term is the identity matrix. That plays the role of 1. Okay? That's the identity matrix. In place of little a, I'm going to put big A. So n by n identity plus n by n a times a scalar divided by a scalar, that still works. Okay? In place of a to the a squared, I'll put big A squared. I can take an n by n matrix and square it, and cube it, and fourth power, etc. So I get this, plus a times t over 1 factorial, a squared, t squared over 2 factorial. I'll just write out a few of them. But I think you get the hint. Plus a to the k, t to the k over k factorial plus dot, dot, dot. So we just take the Taylor series for the scalar exponential. In every place we had a little a, we put a big A where it's an n by n matrix. So this is the sum, k equals 0 to infinity, a to the k, t to the k over k factorial. So that looks super daunting. It looks terrifying, okay? But it makes sense. Because for a square, we can compute a to the k. So it's just a k times. And if a is n by n, a squared is n by n, a cubed is n by n, etc. Wild, okay? So, you can compute this series by hand for really simple A, and we'll talk about that, okay? But only for really simple A can you evaluate this by hand. Using software, we can compute it quite handily, as we'll see in just a little bit, okay? So, we'll see how to compute this in Julia shortly. Okay, but I think everybody in this room can write a for loop. Okay, and that's what a sum is. And no, you're not going to sum it up to infinity. You'll choose some large n and stop. And we'll see that that works, okay? So everybody in this room can take a matrix, raise it to a power, multiply it by a scalar, and add them up. So there's not a doubt that we could do this. The question is it an object that is interesting and something we can manipulate and understand? And the amazing part is it's going to be super easy to understand what e to the at does when we use eigenvalues and eigenvectors. Okay? So that's going to be the big payoff on Wednesday. We're going to understand this through eigenvalues and eigenvectors. Now, I want to do a side computation. So before we even evaluate this series, I'm going to do something that's even more mind-blowing than writing down what this series is, okay? So this would be d by dt applied to in. Oh, okay. Let me do something here to help you guys out. So let me move this and put, so it's all in one screen. You don't need to copy that. You've already got it on your sheet. So there's the series of n by n matrices that we add up to get what's called the matrix exponential. So if I wanted to differentiate this, I just differentiate it term by term. Okay? And it doesn't depend upon okay, so let's see if what I'm writing down makes sense to you guys. I'm treating the matrices as constants because they just have constants in them, and I'm differentiating the things that depend upon t. So I'm just separating out all of the constants. Then I'm going to do this to a to the k, d by dt of t to the k. And for reasons we'll see in a minute, I'm going to do one more term. Okay, so I just took the power series for e to the at, and I'm differentiating it term by term. In Math 351, they'll prove to you that this makes sense with this particular infinite series. Okay? So this should be the sum of all the derivatives on the right-hand side. Okay, so what do we get? What do I get if I differentiate a constant? 0. Now, if my constant is an n by n matrix, what should I get? You're right. I mean, your intuition is right. It's an n by n zero matrix, okay? Because you just differentiate every single entry in that matrix. They're all constants, okay? So this equals 0n. Cool. Now, I get A. What do I get when I differentiate t? 1, okay? Now, I've got a squared here. What do I get when I differentiate t squared? 2t, right? Now, that 2 that comes down, what do I get if I cancel that with the 2 factorial? What's left over? 1 factorial. Yep. Okay, my a cubed. Whoops, I left out the t. A cubed, I differentiate t cubed, I get 3t squared. But I take the 3 and I cancel the 3 there, and so I get t squared times 1 over 2 factorial. Plus dot, 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 plus, I've got a to the k. I differentiate t to the k, so I get t to the k minus 1, excuse me. I don't know what I was doing there. The k comes down, and I'm left with 1 over k minus 1 factorial. And then I put in one more term. So I've got my a to the k plus 1. I differentiate my monomial. The k plus 1 comes down. I'm left with t to the k. The k plus 1 into the k plus 1 factorial leaves me with k factorial. And then I've got dot, dot, dot. Okay, so this is 0. I can leave that out. Now, notice I have an a here. I have an a times an a here. I have an a times an a squared here. I have an a times an a to the k minus 1 here. I have an a times an a to the k. Look what happens if I factor that out. And be prepared to fall out of your seats, okay? So I've got a. When I factor a out, what do I have left here? It's the same thing as the identity matrix, right? A times the identity is A. Here, I factor A out of A squared. Here, I factor A out. Here, I get a to the k minus 1, t to the k minus 1, k minus 1 factorial. Here, I've got a to the k, t to the k over k factorial. Okay, I know, it's like pulling teeth. I'm dragging you through this derivation, but I want you to understand that it's not magic. Now, when I add up the identity plus at over 1 factorial plus a squared, 2 squared, t squared over 2 factorial, dot, 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 a to the k, t to the k over k factorial plus dot, 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 Isn't that amazing? It is amazing, okay? Just like the scalar exponential, you bring down the little a and thing, it works in the matrix case as well. Totally, okay? The only thing you have to believe is that you can do the differentiation term by term. Okay, so you have to trust me that there's, in a course on real analysis in Math 451, they make that super solid. In Math 216, they don't have the tools to make it solid either. So it's not like we're doing something, a trick that Math 216 could handle and we can't. It's not true. But then why is that like totally awesome? Okay, so where was my thing? Okay. Okay, we're going to do some more work and stuff, but let's just play with what we've kind of figured out. We know how to compute this thing. Well, no, I'll show you in Julia that it's like this. It's not hard. So computing it numerically will be easy, and then we'll understand analytically a little bit. But just with what we've done, if I plug in T0 here, I get T0 minus T0, and e to the 0 matrix is the identity. Okay, so T0 minus T0, this is identity times X0. It satisfies the initial condition. And then when we calculate phi dot, the A comes down and we satisfy the ODE. So we'll write all this stuff out on Wednesday. But this is our solution. Come on. Okay, so the fact that d by dt of e to the at is a times at will give us that the matrix exponential solves linear differential equations. So we want to understand how to compute the matrix exponential. And understand its qualitative properties. Okay, so this little calculation here that d by dt, e to the at, you can just bring the a down, just like you would in the scalar case, means e to the at times x0 is the solution to x dot equals ax. Okay. Let me see if my vocarium is still running, or after all this time it's timed out. It's probably timed out, but I can restart it and you guys can. Ooh, kernel is ready. I can't believe that. Okay, understanding the matrix exponential in Julia. Okay, so there's the power series, and we know how to create identity matrices, and we know how to raise matrices to a power, and we know how to add up matrices. So we know how to compute this. Okay, so the first thing I want to show is e to the at computed in closed form for a very simple matrix, 0, 1, minus 1, 0. And I claim that e to the at is cosine t sine t minus sine t cosine t, which you may recognize as a rotation matrix from Rob 101. You may. Okay? It is. Okay? It is a rotation matrix, so it just rotates things. It doesn't change the length of vectors. Okay? So, in the textbook, we use the power series for cosine and sine to actually show this. Okay, we actually evaluate the power series in closed form. It's just, but that's kind of grungy. What I'm going to do is just show you numerically. Okay, so I'm going to take the matrix. I'm going to take a range of t from 0 to 4 pi and do 100 different values. And then I'm going to use the Julia command for computing the exponential. If you were in MATLAB, you would have to put a little m here because MATLAB is not typed, and it would apply the exponential to every entry of the matrix. But the exponential of 0 would be 1, and that's not what we're seeing here, okay? And the exponential of 1 would be e to the t, okay? We're not expecting, and so the matrix exponential is not the exponential of each of the terms, okay? It's much more interesting than that. So we'll just take the exponential, and because Julia is typed, when an n by n matrix is put in here, it automatically computes the matrix power series, okay? And all this says is to compute it for all ti's in this range t. So that's called a comprehension, I believe, in Julia. I don't use them very much, but I used it here. The rotation matrix was cosine sine minus sine cosine. We evaluate it for all t in that range. And then we're just going to plot them. And when you plot them, all the entries, they line up, okay? So, Julia computes the matrix exponential, the power series of A for each value of time, so we did it for 100 of them. And then we computed evaluated the rotation matrix, and we plotted them, and we got the same thing. So, okay, so that's one way. The book has a much more analytical solution that e to the at is cosine t, sine t, etc. Let's do another easy one. Let's suppose the matrix is diagonal. Well, then the square is easy to compute. You just square the entries on the diagonal, and you still get zeros on the off-diagonal terms. And when you do the kth power, you get the same thing. People believe that? Yeah. Okay. So now we plug that information into this power series. And so the first term is the identity. The second term is the diagonal matrix A1, A2 times T, dot, 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 A's this diagonal matrix to power K times T to the K over K factorial. And you recognize this is 1 plus A11T plus A11 t squared over 2 factorial dot 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 A11 to power k t to the k over k factorial dot dot dot. That is the power series for e to the A11t. Now these zeros plus 0 plus 0 plus 0, that gives you 0. So e to the at is not exponential of each of the terms of the matrix. It's really this power series. You have to take the matrix, square it, cube it, fourth it, fifth it, sixth it, 27th it, times t to the 27 over 27 factorial. You have to add those all up. It's a power series. Computing these things by hand is not what you want to do. But computing it like this, that's not a problem. Okay? But you can see here, the matrix exponential of a diagonal matrix is a diagonal matrix, and it's got the matrix exponentials on the diagonal. So for simple things like diagonal matrices, you can do this thing in closed form. Okay? Oh, I know my kernel is disconnected. And so all of my output went away? It did. Okay. End lab. You want to end the lab? No, I don't. Okay. Yes, my lab is now terminated, just like you guys see. I suffer just like you do. Come on, stop spinning. You will stop spinning. Kernel is disconnected. Kernel is initializing. My lab is now ready, and we're running this cell. Okay. Run, please, run. Walk. Okay. So Julia has a built-in function, and it evaluated it for this diagonal matrix. And what was the matrix? Oh, e to the 1.5, and then minus 3. I took t to be 3, so 4.5 exponential and minus 9 exponential. There you go. You get this diagonal matrix. And then I just did the power series, and I played around with it, and n equals 40. I've got things matched out to 6 digits or 7 digits or something. Okay, so all Julia's doing is very, 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 very fast version of this. It's just of doing the power series, okay? It's just adding it all up. If you have a bigger matrix and it's diagonal, the story does not change. And I'm putting these as lambdas like we use for eigenvalues for a reason that we'll see on Wednesday. But e to the diagonal matrix t is just the diagonal matrix of all of the exponentials. It's the same proof as we did for the 2 by 2. And this is doing it for a 5 by 5 matrix. Here's some random diagonal matrix. There's A times T. We applied Julia's exponential matrix, exponential function to this, and there's the exponentials of the individual entries. I just extracted the diagonals, and those are the same as the as if I had computed the exponential of the diagonals. It's the same thing. So E to a diagonal matrix is diagonal matrix E to the entries. And that's all that this says here. And this is just the last thing, and we stop. exp of A is not equal to broadcasting exponential applied to A. Remember, Julia, broadcasting, that exponentiates every term. And here that would be e to the 0, which is 1, and e to the 1, which is e, and e to the minus 1, etc. And if you go and play, it just takes you through that. And we'll come back, we'll start here on Wednesday, we'll review the matrix exponential, and we'll do this derivative calculation symbolically, just to help us to be happy that we can differentiate a matrix exponential. But it's true, d by dt, exp of at is a times this. And just like with the scalar, it doesn't matter which side you take the a down. You can prove it here, though we never use it, so it doesn't matter. So, thank you. We'll stop here. We'll pick it back up, and we'll do more with eigenvalues and eigenvectors, and I think you'll find that enlightening. We'll see. It'll either be lightning and it's hitting you in the rear end, or it'll be enlightening and the light bulbs will start going off. We'll see.